Yes, thanks for the introduction. So today I would love to talk about a bit on the multi-agent learning. And in fact, I've been talking about this subject for a while. So adding quite a few things happening in our lab. And for people who already listen somewhere, attend some of the lecture elsewhere, maybe they probably don't really know the things that I'm going to talk about. But I would also cover a few new stuff that we have been working on for the last few months also. So this is my personal view on this progress of AI, in particular machine learning, where the task can be classified into pattern recognition and decision making. And I see a lot of application, and in fact migrate from the pattern recognition to decision making. So this is not only from application perspective, but also from theoretical research on all these learning problems. Just try to give you a sort of big picture about the difference between them. So the pattern recognition is sort of loosely defined in the sense that you try to come in with a mapping from data to knowledge. In this case, if the task is for face detection, then the knowledge is basically tag each of the image as whether there's a face there or not. And the idea is that it should try to find a function which can, hopefully to make a very good prediction about whether face there or not, and try to minimize the error. So for decision making, things would be a bit more complex, is because that you not only to understand the data itself, but also would like to find optimal decision. In other words, sending action back to the data, modify the data. A typical example is the Go chess, but you can also see a lot of application in, for example, control the car, optimize the telecom networks, and also optimize some of the VRP problem, vehicle routing problem in supply chain management. An interesting development for the last couple of years in terms of the learning is that we not only consider a single machine or algorithm, but I think about multiple algorithms, and they might be work together, or they might, when we try to learn, also consider there's another machine they try to learn at the same time. So which we typically call multi-agent decision making. Just give you example here. When you in this warehouse, then you might have multiple bots. They try to finish some of task. So the task could be like a joint task. They work together to accomplish certain task, or they might have a multiple task and they are correlated together. So a typical another example is driverless car case is that you might have two agents try to drive two different cars. They might in some cross, they might meet each other. Therefore, they need to understand or predict the behavior of another car. So the underlying technology or underlying mathematical formulation is reinforced learning, but they can also have other formulation. But I just give example here in terms of how reinforced learning works. So this is in fact, if you're from the control theory community, and it's pretty much try to solve the same problem, but the different reinforced learning here is that it's typically people call it model free. So in other words, you don't really know the system dynamics. In this case, you don't need to know these mechanic hand, arms, the physical dynamics of it. You try to learn from trial and error in order to perform an optimal decision. And so the interesting thing of this is that, in fact, if you compare with the pattern recognition, although they are taking feedback from their learning process, but when they actually are taking actions, it's pretty much similar to the pattern recognition, where you have input image and the output here is the action. So you could still the purpose here is still try to figure out the mapping from the input to the output. So I would say I will talk about this later. In fact, this is a fundamental limitation of all this control theory approach and the reinforcement learning approach, and so I will try to draw it from the cognitive side, from the study that people conducted to understand human brain. And so the multi-agent reinforcement learning, in fact, is nothing but just adding few agents into the environment, and then the difficulty is that we need to sort of looking at interaction among agents through the environment. Although it's a simple extension, but although mathematics is very simple extension, but in practice it's extremely difficult to optimize. And so people always quite a lot of people mentioned that, in fact, we see a lot of IR cases in gaming, but how about the practical application? In fact, there are quite a number of cases that already show that reinforcement learning and also multi-agent reinforcement learning being used and in fact quite successful. But they are so far in the less critical, less safety or risk critical cases. So in other words, those applications are not to worry about the error that they made from the system. For example, in recommender system or in advertising, people has been used for using multi-agent reinforcement learning for solve the bidding problem. But if we go back to the human intelligence, try to compare the multi-agent system and compare to the human intelligence, in fact, or even compare this our machine learning algorithm from deep learning, and find there in fact a huge difference. I'll just give you an example here, and in either English or Chinese, and we just study change the order of the character, either English character or Chinese character. For human brain, it's still can understand the meaning of the sentence, but if you ask machine to do that, any machine that you building up upon this language model would fail. It's because it's that if just understand these text through the order, then it's going to fail. And the human have much clever way to really understand the text and therefore natural language that actually highlight the difference between human intelligence and AI. And so this is sort of another a bottleneck in current decision making. As I mentioned that in some of these less safety critical cases, we see a lot of successful cases for reinforcement learning. But in these like driverless car cases, because if you make any mistake in terms of decision making, and they would be cause casualty or loss huge economic loss. So in all these cases, and the reinforcement learning need to tremendous research in order to make it work. So this is our recent work on robustness of reinforcement learning. And in a typical reinforced learning algorithm, for example, in this case, I think it's a PPO. And if you change the system dynamics a little bit, you can find that then the model would fail. And so the higher value, this more red, and then actually will give higher reward. And you will see that if you changing a little bit in terms of system dynamics, and anything trend upon that, would you apply in different sort of environment that would they will fail. So we basically provide some kind of training solutions, making use of min-max kind of methodology. And you can find that if we do that training, and during the training, the environment already gave them various of setting to the learner, and therefore, if you change this system dynamics in certain region, and in certain range, and this algorithm would still reliably work in the situation. So I think that actually showed that, in fact, reinforced learning is certainly would be quite useful in some of the safety critical cases, and as long as we provide a better, training methodology to that. So that call, theoretical research on how to properly train these, decision-making algorithms. So one particular area is really making use of, multi-agent training. Consider there's another agent, maybe that one try to sort of minimize the reward that you try to maximize, therefore provide much robustly training method. So let's take the driving as an example. I just try to understand how human brains work. Then we could reflect on that, and maybe can make use of some of these, our findings for human brain, and then therefore use it for our research and use it for developed a better AI. So when people drive, in fact, we could have two type of decision making. On one hand, if you drive in a very familiar environment, for example, if you drive from home to your workplace, and in fact, people can drive while taking their mobile phone or have some conversation with other people with no problem. Of course, I don't encourage you to do that, but people certainly have the capability of doing it. However, if you are driving in an unfamiliar area, and then the things become more complicated, and then you would certainly need to put your attention in your driving, and with your consciousness, and that would actually help with your consciousness and the focus on your driving. And if I ask you, and when you after you arrive at the destination, and ask you to recall what happens during the driving, you can clearly remember, where is the cross and where is the red line, etc., etc. But in the former cases, if you drive in an unconscious way, taking a phone call with somebody else, then if I ask, whether you cross certain, street or something, then you probably can't remember. So that highlights that there's two ways to make a decision in human brains. And in fact, that's true. And there's some underlying reason behind it. So we can look at the human memories and see how it works. And on the right side, there's a procedural memory. So the one that are driving without consciousness, aware, and in fact, will be based on or active use of this procedural memory. So people typically talking about this muscle memory, and in fact the mechanism is in fact embedding into the procedural memory, that you sort of memorize certain procedure, certain rules. For example, if you are familiar with some roads, and in fact, you can make use of this procedural memory to help you to take action. However, this procedural memory is implicit. In other words, you are not consciously, say, able to access to it. Therefore, that's the reason why you can't remember what's happening. Where on the left side, those memories are responsible for when you are consciously aware. So you can make use of those memories to help you, in fact, to make a decision when you are conscious. So these are the accessible when you consciously aware. So therefore, that's why I explained why you remember and the experience that you had when you drive carefully. So in fact, researchers, cognitive scientists have conducted a lot of experiments to understand consciousness, and in fact try to allocate what kind of neuron were activated when you're consciously aware. So they're using EEG, also some scanning method to scan the human brains and when ask questions. So they find that when you conscious control, and this whole human brain sort of activated, and there's multiple places they are activated. Whereas in this unconscious control, you don't. Only a small portion of that are activated. So that shows, in fact, that there's two type of there's strong evidence. There's two type of control in human brain. So basically, taking that, and when we looking back to the neural network, and you will find that so these things become different. There's a theory called integrated information. The integrated information theory, it tries to explain this human consciousness, and they basically show they're coming with some sort of a measurement. This measurement and tell us how likely this neural network would give rise to the consciousness. Okay, although this is still a theory, there's no proof whether this kind of measurement is, correlated with consciousness. But they provide kind of indication, what kind of information has been integrated in the neural network mathematically. So look at the right side. These are the feed-forward network. And if you measure this integrated information, in fact, it's zero. But if you look at the left side, and with certain, connection, particularly the circling around kind of connection in the neural level, then when you measure the integrated information, in fact, there are quite a few sort of integrated information measured. So that shows that any feed-forward neural network that we are using, particularly for example, vision task, convolutional neural nets. In fact, there's no way they would give rise to the consciousness when you compare to the human brain. So that suggests that we perhaps need to have a better neural network structure in order to induce some sort of human level intelligence. So this is sort of experiment done by neuroscientists, and they actually in the simple cases, they try to do a simulation. And sorry, so my son. So in this simple setting, I think what they did was that they tried to define a digital devices, and using the digital device try to pass the maze. It's very, very simple setting. And in this setting, and they try to say, I don't have any sort of neural network connection. I try to learn this connection between neurons, and using new evolution strategy to try to come up with a neural network structure. And they find that at a certain generation, and this fitness increased largely when this neural network connection have the loop in between. So that suggests that if we need to have building some kind of memory and building some kind of loop in our neural network structure in order to have a better capability and to sort of to complete certain tasks. So this is our engineering approach to this case, and we sort of modify this current way to approach reinforcement learning by consider some of the missing parts as we started human brain. For example, what we adding here is that we need to add in this word model. We need to add in the component model. So in other words, we need to not a model-free solution, but model-based reinforcement learning. But also we need to have some sort of memory looping in our state in order to build up this agent state where the current formulation effects also missing as well. So we also need to add a design for each individual agent in order to basically say each agent, they might have come with their kind of rewards when they conduct the task. At the moment, is this design of this reward is rather sort of arbitrary. And lastly, there's some meta recognition. So in other words, the big I question. So what is the itself? So I think that's also missing in the current formulation. And so one of the potential directions is really sort of making use of Bayesian inference to sort of building a sort of understand the uncertainty of the decision making in order to sort of build a sort of uncertainty. Because one of these interesting things about self is they can able to evaluate and conduct certain assessment about the agent's own action and their performance before actually taking action. So I think the current sort of formulation of agent mining, in fact, didn't have that. So I think it will be very interesting to include that. So with this in mind, I would like to quickly go through some of the research we've been done for the last few years also in order to achieve the goal that I mentioned. So the emerged behavior is what we try to understand is that given the fact that the neural network is the best tools that we got so far in order to, for example, making predictions and to realize the things that we want to realize. Then the question keeps that with that little intelligence, from the neural network, what if we to build up a population of agents to see their behavior, whether that would be consistent with what happened in nature. So this is a result from biology, where people try to measure the two populations. One's a predator, another is prey, and to see the population correlation between them. In fact, there's a strong correlation in terms of population size. And if you plot the size, and you can find, in fact, they kind of have a circling loop between the population size. And so we're using very simple and reinforcement learning, like a Q-learning, but we managed to make it. We managed to train 1 million agents using this simple single agent approach. And I'm putting in this scenario where we got a predator and we got a prey, and they are sort of correlated in the sense the predator try to hunt the prey and the prey try to sort of avoid and also try to sort of find the food in order to survive. So the reward is basically whether they are able to survive. And they don't really have knowledge of whether, eating or food, but through the interaction, through the giving them the reward, and they will eventually learn, for example, for predator, they will eventually learn how to hunt the prey. So equally, the prey know how to avoid the predator and also actually how to take food, where to allocate the food. So I think this is very interesting is that they provide kind of setting where we didn't design the rules, right? We didn't design rules, but they can somehow learn by giving them the reward. I think maybe this opened up very interesting research to help biology to understand nature and sort of compare with that. So one of the things we find that is when we train this those two populations and try to understand and try to see their behavior, and then we find that in fact they also, in terms of the population size, they also had the similar circling patterns as happening in the nature. So that basically showed that this artificial population and some of behavior, in fact, might emerge naturally and in fact consistent with what we observed in the nature. So you can do a lot of things, like you can understand the communication, you can understand the language. So I'll just give you one example of that. So the second research direction we're working on is what we call agent modeling agent. So in other words, that we need to build a model of the world, try to understand the environment, but also importantly, try to understand the other agent. So the theory of mind, in fact, was designed to understand how human model or mind other people. So this is hugely important. I can use in this driving as an example here. So in UK, we have this called so-called magic roundabout. Is that there are a lot of different sort of a circle you can see, and in order to pass it, extremely difficult because you need to observe others and predict their behavior. And because the people already in the circle, in the roundabout, they have a priority. So they have higher priority. So you need to based on their behavior and do the best response, and then make a decision and act accordingly. So so think about this. If we want to design a computer to drive the car past this kind of roundabout, they definitely need to build some kind of model to understand other cars, and also need to do in a very quick way, and do the assessment, and then based on that to plan their own decision. So in order to do that, so as I mentioned, there's a pattern recognition task and also decision making task. So the pattern recognition task, typically you can using statistical solutions, and you can also using some of the prediction solutions. But decision making typically is framed as a control problem, more or less kind of optimization problem. But back into 60s, Kalman published a pioneer paper to establish the duality between estimation and control problem. So in other words, we can in fact using estimation, whatever we use for estimation for pattern recognition, can apply those techniques for our controlling problem as well. So in our case, in fact, we can use an estimation or inference to not only for the single agent control, but also for the multi-agent control. So apology for the mathematics here. So I just want to illustrate here. In fact, we can using inference to building up kind of component model. So for example, here, we can in fact using the inference to sort of understand, given certain context here, the S, and what kind of action the opponent, the other agent would have. Then condition on that, and also condition on the current state, and then I will come in with my policy to say, this is what happens for the opponent, and then I will provide my action in such a way would maximize my, utility or reward. So by explicitly building up these opponents, and we're able to sort of realize the cases that we would make a prediction of assessment about opponent, and condition on that make our optimal decision. And in fact, the things are more complicated than that, because if another agent is also intelligent, that means they also observe you and also try to, understand your behavior, and they provide the best response as well. So that created a kind of recursive reasoning between them. So in fact, there are different levels of recursive reasoning. So they might also think about your action and also realize you also observe themselves. So they create some sort of a level 2 kind of reasoning. And in fact, people studied, and human can be able to, by average, can take a 1.5 level of level thinking. So when we design an agent, and that would sort of interact with other agents. So some of the agents are less complicated due to certain constraint they have. For example, they might have some constraint in terms of computing power. They might have constraint in there of CPU times. So the recursive level of intelligence would be sort of low. You might have a more powerful agent, therefore the level of reasoning will be high. So the question is that how can we sort of respond in that kind of thinking? So you can actually mix this kind of level K and construct kind of a generalized recursive reasoning methodology. And you can actually train the agent in certain environment. Then you sample this level K of agent from a pool of agent. Then you can say, based on this, you can find a very good way to model this bounded rationality in the multi-agent setting. So another interesting things that we've been working on is try to understand what kind of learning algorithm we can use in the multi-agent setting. So in a typical single agent setting, I think in the previous talk, Professor Zhu mentioned about deep learning. So they typically using gradient descent or some variant of gradient descent atom to optimize the neural network. But if you're just using gradient solutions for multi-agent setting, and in this case, to show that in a very simple normal phone game, you're never going to converge to the Nash equilibrium, which is in the center of this graph. But using the kind of recursive thinking, in fact, and you can come in with kind of a clever way to learn simultaneously between these two agents. Therefore, you can quickly converge, as we show, you can quickly converge to the Nash equilibrium. So this is an agent model agent. And the next topic is about communication. So this is what we did a few years back, is to really, then when you have a multiple agents, and sometimes this agent has more than two, let's say you have 10, in this case, StarCraft case, you might have 20 agents. And then if you consider as a single agent, then things become much more complex, right? Each of them need to take action. So you could come with a simple structure. For example, consider each agent, they take an action alone, but they allow to communicate. So we're using this bidirectional neural network to have a much more efficient way to communicate, and then you find that, and they would let agent to figure out what kind of information you need to share among them. So we can also using multi-agent to solve some coordination problem. This is a very simple game setting where you got two agents marked as these red dots here. So we intentionally to design a particular case to study the collaboration. So we allow in this case the blue dots, they know where the next target is. So the rectangle are the target nodes that we need another dot to reach to the target node. So the another dot, the black one, they didn't know the destination, where to go. But if they achieve that goal, and both agents would get joint reward. So that basically say one of the agents can observe, know where the destination is. One agent can walk, but they don't know destination is. Force them to somehow communicate. But in this case, we don't even give them the communication channel whatsoever. We just want to see, in this situation, how they can actually learn to collaborate together. So it turned out this agent find a very clever way to doing that, is that this red agent, for this case, they basically using their action to guide the black agent to the destination. The black agents basically observe the blue agent's movement and follow them to reach to their destination. So that basically showed that, in fact, agents can be able to using some kind of information share between them and make use of that information to sort of implicitly communicate. So we apply this algorithm and using it for solve bridge card game. In particular, in the first in the first part of this bridge card game, where it's typically people bidding to figure out this bidding strategy, and we allow agents to collaborate in that setting. In fact, find that they making use of bidding strategy, what kind of card they bid in order to make use of that information to communicate, to learn their hands. So it's provide a very effective way for them to communicate. So the agent can also collaborate in different ways. For example, here we're looking at a setting is sometimes with the agent, they only have one agent, but they have a multiple objective. So in this case, we can in fact making use practical efficiency to solve a problem. In fact, you can building this kind of multi-object learning into the existing reinforcement learning framework, therefore can solve the problem. And this work is we basically argue that not all the multi-agent learning problem has to be Nash equilibrium. In fact, if we want to combine this research game theory and also machine learning, and perhaps Nash equilibrium not necessary to be, in some cases, not necessary to be ideal solution concept. So this is an example we gave. For example, in some of the game, maybe it's better solved if we identify a leader, a follower. So the leader basically come up with their policy, have more information, therefore they can come up with their policy. And then the follower basically to observe the leader's action and provide the best response to that. And so in this work, we provide one of the earliest formulation in the stochastic game, making use of Stackberg equilibrium rather than Nash equilibrium. We'll provide a Q-learning solution, in fact, and also provide the convergence proof. So the this is a work that we it's a general sum game. So I can tell a bit about the current research on this general sum game, in particular the learning solutions. So people have been for the last couple of years, people have been, really dedicated effort on trying to understand these. How can we come up with a learning algorithm for a game setting? So this min-max zero sum game, in fact, can be straightforward formulate because there's very clear theoretical result in the past in terms of polynomial term algorithm for zero sum game. But for the general sum game, in particular, general sum stochastic game has been very, very difficult to provide theoretical sound learning algorithm. So one of the approach we've been thinking about is to approximate the a general game by using some games that we know. So we make use of these potential functions that being heavily studied in physics to do that. So here I'll give you an example. So this is the potential function defined in the physics. So in fact, there's a relationship between a single potential function and a multiple reward function that typically observed. Typically, we have in this in the game setting. So we can, in fact, using the potential function to represent the game. The benefit of that, in fact, we can just have one single function. If we know this potential function, we know everything about this game. And then when we know that, and then we can based on this mechanism, we can actually learn this potential function, and therefore using this potential function to approximate the original stochastic game. So just to give you an example here, let's say on the left side, this is a prison dilemma, sort of a reward structure in a very simple normal form game. And then in fact, you can using just 4 parameter potential function to represent this original prison dilemma rewards. So when you make use of that, then you can become very simple representation. So in the stochastic game case, then you don't need to solve the original stochastic game anymore. But what you can do is that you can make use of this underlying MDP to approximate the stochastic game. So we conduct one of the earliest work on that and provide quite efficient sort of a learning algorithm. So this is still ongoing work. And so our initial results show that if you compare to, like, for example, using MADDPT or English single agent learning solutions, you find that this approximate provides very quick way to learn a typical stochastic game. So at the last, I'm going to talk about this many-agent learning. So in most of multi-agent research, they are focused on 2 agents, but they call it multi-agent. So we think it's not right. So this setting is that think about, suppose you have a large number of agents. How can we come in with efficient way to learn it? So one way to tackle the scalability is really to looking at so-called mean field approximation. So in other words, that we convert this many-body problem into 2-body problem. So we can take the mean or population statistics, the statistics from the population of agent, and for each of agent to provide the best response to that. And then eventually they will convert to the mean field sort of equilibrium. And so then the algorithm would be very quick to converge, and also is a very good way to approximate this original solution. So I give a very simple toy example just to illustrate the underlying mechanism. Suppose that we are having a meeting, and this meeting would start it. Let's say we start at 10. We planned at 10 o'clock. We start the meeting, and but the actual starting time would depend on how many people has already arrived. Let's say in this case, 25% of the population would when arrived, then we basically say we will start the meeting. So each individual participant, they're gonna based on their own reward or their incentive to decide when this should come. So they can come a bit earlier, but obviously the benefit of that, they're gonna obviously don't miss any lecture in the meeting. But on the other hand, the drawback of this is that they have maybe waiting too long. Therefore, they might be impatient. So, but you can come a bit later, or if you came later to the meeting, then the benefit is that you don't need to wait anybody, right? Because the meeting already started, but you missed the game, you missed the meeting. So you try to based on this when this meeting gonna start to sort of provide the best response given this certain objective you got. So this is sort of can be solved by using the sort of mean field inference. So what happens here is that you could start with this t here. This t is the when the meeting gonna start. Suppose the meeting starts at t time, and then based on that, individual gonna decide when they're gonna come. Okay, do the best response. And this tilt is basically the actual arriving time for each individual agent or participant. And you can actually, based on this reward, you can optimize that if you would know when actually the meeting started. So once each individual agent, based on that, to know exactly when they're gonna arrive, then obviously you know the population distribution of population's statistic about when they will arrive, and then therefore you can decide, recalculate when the meeting gonna start. The whole process sort of start again. So people actually prove this is a contractual mapping. Therefore, it converts to the fixed point, and the fixed point is a mean field equilibrium of this problem. So this is a very simple toy example, but with that kind of mechanism, you can apply for various of many agent reinforcement learning problem. For example, in this case, if you devise a Q function in a multi-agent setting, so let's say that J is for a particular agent, and the A is a joint action through all the agents. But suppose you have a population of agents, they have many agents, therefore this is very high dimensional sort of action. So what you can do is that, in fact, you can make use of a mean approximation to approximate that. So in other words, you can take a mean of the population, their mean actions, or any other statistic about other people's behavior, and then each individual and do the best response towards that. And once you got this sort of individual action, you can update your population statistic. And then as we showed that previously, the toy example is this contractual method, therefore they will converge. So with this kind of way, you can solve this many-agent problem. So we did a very experiment actually show that this provides the model-free solution to the icing model experiment, which is in the physics, it's a very popular experiment. And typically they did was as a model-based. In other words, they need to know all these parameters. Right? In this case, we don't. So that concludes our talk. So in summary, what I try to emphasize is that machine decision making is the next AI challenge, and reinforcement learning and multi-agent learning are a really exciting research area toward that goal. However, there's a need to revolutionize the reinforcement learning formulation and also multi-agent formulation. We need a new theory. Perhaps this theory would be coming from our understanding of how human brains works. For example, what kind of situation give rise to the consciousness, what mechanism underlie the consciousness. Therefore, coming is a maybe better theory, and that theory would help us to, build a computerized model. Right, this computerized model would create a kind of new theory of computer science. That new theory of computer science would have influence and impact on these, practical application from reinforcement learning and multi-agent learning. Thanks for your attention.
Yeah, thank you very much for the wonderful talk. And we have quite some questions here. And one question says, what role does consciousness play in decision making, and how consciousness play a crucial role in implementing human level intelligence?
Okay, so this is a very interesting question. I'm not sure whether I would completely have the answer, but maybe I'm not really the best person to answer that, but I'll try to answer that question. So what is the role in consciousness in terms of decision making? So I try to sort of go back to the slides. So this is sort of a study from neuroscience, and people studied that, and they give people certain, control task, and then they measure this neural activity in human brain, and they find that in some of the control tasks that need people to consciously aware the task. So in other words, there's a specific definition of consciousness, in fact, in neuroscience. Basically, if the people can recall what are happening, that means they are consciously aware. So I think neuroscientists, in fact, can conduct various of, provide various of tasks, allow them to, or the subject, to basically verify they are consciously aware while they're doing this action. So therefore, it's a conscious control. So in this setting, they measure the brain activity, the neural activity, and they find that, in fact, it's not a things going on. In fact, there's a sort of feedback things happening and also feed-forward things happening in human brain. So that basically suggests that those neurons, there's not just single feed forward in order to perform the task. In fact, there's a looping things going wrong. That's why I think it's, same thing here is that when you construct this kind of simple task, like in this sort of a digital mouse, they try to pass the maze. In this case, if they are very successful, even in the simple task, they need to have some kind of loop behavior in their neural connections. So I think if the single message wanna pass here is that this neuron, they are connected to each other. When they make this consciousness control, and there's a feed-forward loop and also feedback loop. But people don't really see it in the consciousness tasks, or in the task that you don't need to conscious aware, as in only small portion of the human brain or neurons sort of being activated. Hopefully I can answer that question. What was the second question, Professor Chen?
Yeah, the second question, how would consciousness play a crucial role in implementing human level intelligence?
So, sorry, can you say it again? or miss that?
So it says basically says the consciousness. How would it play like from machine intelligence way?
Yes.
How would it play a crucial role in implement human level intelligence?
Yes, I think that was very interesting question, and so I think there's a lot of argument about consciousness because nobody really understands what it is yet, and at least there's no proof on any theory about consciousness. But I think it's a very interesting way to think about that way, and particularly looking at some of the computerized model to understand that the mechanism behind it. For example, in this integrated information theory, and I think it is not a necessary condition. So perhaps it's a necessary condition for consciousness, but not necessarily sufficient. For example, if we measure this integrated information, in fact, the thermostat would have consciousness given this measure because they have the feedback loop, and therefore, when you measure the integrated information, there's some value on that. So I don't say this consciousness is the same or equivalent to intelligence, but I think consciousness maybe is a necessary condition to have a human level intelligence, or can give rise to human level intelligence. So I think in the driving case, if we just have the feed-forward neural network, I don't think this would work, because in these far more complex cases, in all those far more complex cases, particularly the observation, they are non-stationary. So that require any decision maker to have a capability of thinking. So when I say thinking, is that not just a feed-forward this neural network. But the feed-forward this neural network is still a rule, right? But this still rule, implicit rule, is encoded. Being encoded is with this nonlinear, complex, implicit function mapping from neural network. But I think need a kind of feedback loop in this case is that when I observe something, I need to retrospective to think about what's happening there, right? I need to have sort of information circling around either in the brain or the agent's brain to do some sort of some kind of analysis, if you like, or do some sort of planning. And then we have with this sort of feedback and feed forward, and maybe then give rise to the thinking, right? Give rise to thinking, therefore, would be able to accommodate a much better way to do intelligence, if you like.
Yeah, thank you. Actually, we still have quite some questions, but the time's late. So maybe we'll send the questions to our keynote speaker, and he can send some back. We'll post it. So, so today's talks are all finished. So tomorrow we start at 9 a.m. and thank you all.
Thanks.